Lesson 1, Part 2 for statistics. I'm going to be trying to make this one again. This will be like the 5th time I've recorded this stupid thing. I'm currently hiding from my kids outside, so you're going to hear some random ambient noise, but hopefully you won't hear children interrupting. I left off by talking about the name of this interval that we're going to be making, and that there needs to be some multiplier that's a t critical value but not a z critical value. So the critical value t star has the same interpretation as z star. So we're measuring how many standard errors. This is the multiplier part. How far we need to be spreading our interval apart to make sure we get the capture rate that matches the level of confidence. So basically, if we use z star, they end up just too short and you're going to miss more than you're supposed to. Using t star will make them longer so that you miss less frequently. So we are going to specify a particular distribution because there are a lot of t distributions, and we're going to specify its degrees of freedoms. Because the t distribution is a family of curves. It's not just one, like the standard normal curve is just the one. But we are going to state df, degrees of freedom, by taking our sample size and subtracting 1 from it. So I have on here a couple of the t distribution curves along with a normal distribution. We can see the normal distribution here in black, so it's the one that is at the top, but if you follow it down, it ends up the lowest. It ends up coming closest to the horizontal bar at these particular numbers of -1, -2, -3. So the thing is, if you have a different degree of freedom, if you have different degrees of freedoms, you get different curves. But if I point out like let's look at the green one, let's say. So it's the one that's 2 below my normal curve. When it comes here, it's up higher. So when we know we have a certain area in a tail that sets some z star value, we're going to have a bigger, or technically smaller, t star value that would have the exact same area just because of how it's formed. All that to say, your t star values are always going to be larger than the corresponding it already says then. Larger than the corresponding z star critical values for any level of confidence, which is what's going to make these intervals wider. And we're going to find them from a table. You could use a table for the inverse norm, but we typically use our calculator for it. We're going to use our table to find t star values, partially because some people will have to use this. So, for example, whenever we did that simulation with the tomatoes using that applet, there was a sample size of 4, so we would have 3 degrees of freedom for this one. So if you look at a t distribution table, they put degrees of freedom along the left-hand side, and that tells you which row that you're going to be in. Excuse me. And then at the top, they put the area in the tails. So by that I mean, if I want a 99% capture rate, there would be 99% between these two critical values, which leaves 1% not to be between them. Half of 1% is half of a percent. So I could look at the column of 0.005, but if you look at the bottom, it'll also tell you already what the corresponding confidence level is. Where this column intercepts the row of degrees of freedom of 3, that gets us our critical value of 5.841. So these are the cutoff lines that would put 99% of the area between it on this particular t distribution. Now, not every degree of freedom will be listed on this one. So the rule is you are to use the biggest one possible, but it has to be less than the actual correct one. If the correct one doesn't show up, essentially round down. Sorry. I'll show you what I mean by that in a second. But if you round up, so for example, if I look here, let's say I was supposed to be using, I don't know how I want to say this. If I needed, let's say 2.5. If I round up to 3, I get a number that's actually smaller than if I round down. So by doing this, I'll make sure I have the correct width. If I round technically up, this critical value will be too small to have the level of confidence that I'm trying to use. So to do this, if I have a simple random sample of size 12, I have 11 degrees of freedom. And if 95% of the area is in the center, that leaves 2.5% to be in each tail, because it's half the complement of 95%. So I could look at 0.025, which is here, or I could look, I put the whole T distribution table on here so you could see the whole thing. The bottom again has the confidence level. Theoretically, if you took the AP test, they would give you this table. Since that's now going to be an online test, I have no idea how they're going to do that for us, but whatever. At some point, if you need it, this is how you use the table. So I'm in this column. I just said 11 degrees of freedom. Did I say 11 degrees of freedom? I did. So I'm in this row. This row meets this column at 2.201. So I'd have a T star critical value at 2.201. So now the next problem, 90% confidence from a sample of size 48. So I'd have 47 degrees of freedom. When you go to look at that on the table, you're not going to see it. But you will see the specified level of confidence of 90%. It is here. So basically, it's a decision between these two. They're really close to each other. It's not going to be that dramatic of a difference. But again, if you round 47 up, then you're going to get too small of a multiplier to get your capture rate that you actually want. So go down. Go down to the next available one that's an option. So 1.684. There's another way to do this. And so if you do this way, you need just to say using the T distribution table, this is what we got. But you could also use a calculator for either of these. It should be wherever you found inverse norm. So for those of you with Inspires, or those of you with, what am I trying to do? The Casio, you're on your own. Google it. Everybody else, the place we found inverse norm, which should be second distributions, inverse norm is on there. It should be right below inverse norm. Inverse T is what you're going to see. First thing it wants is the area. So we said if that 95% one, we had 2.5% in each tail, and we said we had 11 degrees of freedom. So if we tell our calculator those two things, we still get 2.201. It rounds to about the same thing. When you have the actual degree of freedom off the chart, it should be identical or close to it. For the next one, it was 90% 90% confident. So if 90% is in the center of the curve, that leaves us 5% in each tail, half of the complement of 90. And that one, we had 47. Now, there's not a 47 on the table, but we can do 47 using technology. T-table stuff usually takes longer to calculate, and I see 1.678 for this one. So using a calculator, it is slightly different sometimes. So that's why you should specify which one you're using. So it's not just some random number that I can't tell how you got it. As always, statistics isn't super picky on what you do to get your answer, as long as you say why you did it and how you got it. So we fixed the issue with having not wide enough intervals. We fixed the issue with the possible sampling variability and using S instead of sigma. The other thing that people tend to mess up, though, is when you use T and when you use Z for these. So far, Z-star had been everything about proportions. Confidence intervals for proportions, hypothesis testing for proportions. It's proportions. T-star is for means. So if you get a problem that's talking about you're comparing the percent of girls who wore blue to the percent of boys who wore blue, you're talking about proportions. Use Z-star still. But the moment it starts talking about something happening on average, you want to know about this average or predict this average or test this average, that's when you're going to go back to using T-star, because you're not going to know sigma and you have to. So it's really difference between categorical data and quantitative data. So pay attention to that. When we do these tests, because we're getting really close to finally getting to do this test, we're going to have to check our conditions as we always do. Nice thing is, even though this is a different test with a different critical value, first two conditions are still identical. As always, you have to have randomness to do any type of inference. So you have to have some random selection. That's not different. Because you are sampling without replacement, almost always, the 10% condition is going to let us pretend that our calculations are going to be independent, essentially, even though they're not. So mathematically, technically independent. So we'll still check that. But if you remember, the large counts was to make sure that we had a normal distribution, and it was looking for the predicted or the number of successes who would say yes to some question. That has not much meaning when we talk about means. Like, how many of you would say yes if I said, how tall are you? That doesn't make sense. So instead, our third condition is making sure still that we're normally distributed, but it's different when we talk about means. Excuse me. Way back when we used to go to school, we had gone up in the front of the board one day. Instead of putting p hats, I made you put x bars, and we started noticing that sometimes the sampling distribution as sample means turned out normally distributed. There were two ways that could happen. That's what's encompassed in the normal/large sample condition. So in order for it to be appropriate to use this t distribution, you got to check that. There are two ways for this to happen. So if your sample size is small, which we're going to go ahead and set your threshold, if it's less than 30, what you're going to have to do is graph your sample data and just say, is it plausible that this could come from a normal population? And the only way we can really say that is if there's no strong skewness that we're seeing in the sample, and also there's no outliers that we're seeing in the sample. So it still might be the population's not normal, but it's less likely if our sample isn't looking abnormal. So then we could go ahead and say yes, but you're going to have to graph the data. That's the annoying part about this condition, is sometimes you got to graph some data. If your sample size is large, so again, if you are collecting a sample of size 30 or more, you can go ahead and use your t-star value no matter what the population distribution is. We had said, I don't even remember what unit, but back when we were in school, that no matter what, you sample a large enough sample size, your sampling distribution of sample means will still be approximately normal. So the three ways for this last condition, which is the normal/large counts condition. There are three things that could help you meet this condition. The first one is just writing this word normal here, because if your population is normal, you say, oh, well, I'm done. They said the population is normal, move on. If they don't say that, but they say your sample size is large, cool, you're done. If you fail both of those, then you're going to have to look at the graph of the sample data and just say that it's plausible that the population could be normal because of not seeing skewness or outliers. So that's the only new thing for checking our conditions here. The 10% condition still looks the same, where you're checking that n is less than 10% your population. So that won't be any different. So on example 2, we're going to look at just the normal large sample condition because it's the only one that's new, and then we're going to actually go through and make a confidence interval based off of some example. I'm going to get some water so I don't keep